increase the volume of my USB microphone. Yeah. And what else do I want? I want to listen to songs that won't get me in trouble. So soundtracks normally go that way. All right. Okay, so this is pretty cool. Everything you see me writing is pretty on point. You don't actually... Okay. So, first things first, we want to answer some questions. So, why don't we move this a little bit over? Nope. I think it's display capture, right? No, it's window capture. This right here. Okay. So we want the first question. Okay. So we gotta look at our questions. So let's look for this right here. Okay, so we are gonna go over a few questions. Okay. Okay, so we are going to go over questions, and then what we're going to do is we're going to use LaTeX to create it. One second. I wonder if I can put this way over here, because yeah, I can. Then what I'll do is I'll set this up so that you guys can see my other stuff, which is also pretty cool. Okay. Okay, and then what we'll do is we'll just do display capture, and we'll change this to my main monitor. Let's see. Nope. There we go. Now, we're gonna stretch this so that you guys can actually just see it. So, this is LaTeX, and what it does is it turns things into, well, things. Oh, this is assignment 3. No, this is my actual assignment. Okay, so as you can see, I've already kind of started doing the work here. Right here. Ooh, my big fat head's in the way. Let's put my head somewhere. Well, actually, I could just go up more. Okay, as you can see here, is that I've already solved one of these. Okay, so what it is asking is we want 2 plus I to the square root of 3 is algebraic over Q. Okay, and that's where we let this. And so what I did was I let Z equal 2 plus I to the square root of 3, which is a complex number, and then we just did some algebra. What we did was we subtracted 2 from both sides, and then we squared both sides. That will get rid of the I, because I becomes -1 when you square it, and then we find out this. So the root is, well, this is the root. So when we do this, we'll get 0, and that's when this is a root of it. So that's how that's the polynomial that's the root of. Okay, which is pretty simple. Next is we have to go over some pretty difficult questions, and that's what we'll be doing next. Okay, so we have this problem, the second problem. Okay, and it's asking us how can every element be represented such that let's see, is that easy to read? I feel like that's not. So why don't we just zoom in a little bit? Okay, there we go. How can every element of Q adjoin A to alpha be conveniently represented? Right? And based on the information, what that from perusal is we can conveniently represent the all numbers of Q adjoin alpha. So that this is what this is saying. It's isomorphic to Q adjoin, well, not X, Q to the element of X over X4 over plus X plus 2. Which this is essentially saying is if you take an element in Q of X, like let's say 3X, if we try to divide this, if we try to divide this by this, 3X, what we'll end up is we'll have X4 plus X plus 2. And if we say we take Q equaling 1, what can we add to this? What will our remainder be when we have this? So in order to get rid of this, we have to find something such that, how we get rid of this is we have to find something such that the remainder plus this is going to equal this. Now Q doesn't have any characteristics, so that's kind of difficult, right? You can't just get rid of X4 plus X plus 1 or X4 plus X plus 2. So that's where it kind of gets difficult. But essentially what this is asking for this is how can we write this such that it's very easy to see, and how we would do that is based on the definition from perusal, or from the textbook essentially, which is Q of X is going to equal QX plus Q adjoined alpha, where Q is in Q of X, where the degree is less than n. It's not equal to n, it's just less than n. And so that's essentially saying any polynomial with Q of A, or Q alpha, is going to work, is going to be in this adjoined, this enjoyment essentially. Okay, so that is easy to write. We go to our latex. Okay, and what I'm going to do is I'm actually going to increase this so that... Ooh. Let's see if we can increase the size of this, because we kind of want this to be bigger. Okay. Okay, so this shows my code. Okay. So we got to find the problem first of all. Problem 2 is right here, I believe. Yeah, so how can every element of math be conveniently represented? So with latex, what we got to do is we have two problems in this question, so we got to enumerate it. So what we're going to do is we're going to take this and we're going to go begin enumerate. Okay, and then what we're going to do is we're going to end that enumeration. Okay. So essentially what this is saying is anything in between these two will be enumerated. And what enumerate does is essentially just gives it a number. So when I put an item here, like this, there's a cable in my way, so this is actually kind of difficult. 1 second. There's a few cables in my way, which makes this extra difficult. Okay, so wrong way. So item, what this will do is if I click this button up here, this play button. Oh, 1 second. There is a issue. I guess I gotta put something ahead of it? Let's see. No. Begin enumerate, end enumerate. That is correct. Paragraph ended. Enumerate. Enumerate. Yeah, it's... That's all correct. Why is that not working? Oh, because I put it up here. There we go. Okay, so what that'll do is it'll put a number on our styles sheet. 1 second. Okay, that should fix it. So if we come down here and we look over here, what we'll see is this 1 right here. That's literally what that did. I know, it's a lot of work for little things. And then what we're going to do is we're going to add this quest, which is we've defined as bolding. So what this is nice is if I say I want how can every element of math be conveniently represented, we're going to put that right in here so that when it shows up on my style sheet, it's nice and bolded. And that's going to work for me because, well, I need it to be. Now, I want to get rid of this white space because, like, I don't need it there. So, now, we just need to represent this in this form right here. And this is what latex is for. So, what we're going to do is we can say that this can be represented like this. So what we'll do is we'll add these math symbols or money symbols to represent a math area, right? Which is nice, it's cool. So we want it to show up. I'm wondering if Q works. I'm pretty sure Q works here just because I've set that up. Let's see. Where is it? It's question 2. Yep. So that works. So I've set that up so that instead of having to use math BBBQ, I can actually just use Q, which is nice. So we want Q alpha. This is for the Greek letter alpha. We're probably going to separate that just a little bit. Okay, and then we want it to equal this bracket to the Q in our Q of X such that the degree, and we're going to say degree, is less than n. We're going to close that bracket. And that's our solution right there for question 2. I'm just going to show that real quick. Now it gets cut off here because it reaches the end of the paper. So how can I solve that? All I can do is I can actually break the line and have it go down by adding double lines. So we're just going to do that real quick and see, check this out. Okay. Nice and easily represented. Q of alpha can be in Q of X, degree less than n. Okay. Wowie, that was simple. Okay, and 1 second, we're gonna put on some, this is nice Donkey Kong music from Donkey Kong 3, but let's go with something, I don't know, maybe Final Fantasy 7, Final Fantasy Crystal Chronicles, that's nice, but Moonlighter always seems to be such a good, like, music in my opinion. Okay. So we've represented it and now we want to move on. So we're just like, we'll add another item. Okay, and we'll bold it again. Okay. Now we want this represented. Okay, so what we want is this. Okay, like this second one right here. And how do we want to represent it? Oh, in the representation above. What is in the representation above? Okay, they said maple will be handy. I wouldn't know how to get at that right away from maple. Okay, so we're just going to bold that again. Okay, see, now it's here. The second line's right here, and it wants us to explain it. So what we're going to do is we're going to go to our tablet right here, and we're going to just write things out, okay? We're actually going to keep that definition because that's actually what we need. Okay, so here's our definition, our convenient definition. What we're going to do is we're actually going to make this smaller so that they get more room to work with. So we have to represent this highlighted portion, and we have to represent it in this form. Okay, so what that's saying is that we have this, some polynomial in Q of x such that we can get this Q of alpha such that this. So this is some polynomial in here, okay? It also can be described like this, because this is our Q of x, and I guess this should be square brackets, so, oh. Okay, so how can we express this in this manner? Either in this way, where we have an isomorphism, or in this convenient way, the shorthand essentially. Okay, that's a very difficult question, and this is why I have such difficulty with this course, because it's not easy to think about, you know. So what we have is Q alpha is isomorphic, that's what this means, is isomorphic to Q of x over x4 plus x plus 2. Okay, well, this is like saying this. This is like saying this. It's 2 over 7 plus alpha over alpha squared plus 3 alpha plus 7. Okay? Or another way to say that is this is being divided by this, or another easy way to describe that would be there's some q plus alpha. Now, the problem with this ideology, I guess, is the fact is we don't know if there is a remainder. We're just kind of assuming there is, right? If we wanted this, though, what would we need? We would need to get rid of this, and then we would need to add something to this and this such that we get this, where we get 1 alpha over and 2 over 7. Okay, well that could be kind of easy. Well, like 1 alpha, we can make r negative 2 alpha. So that makes things a little bit easier. And then on the 2 over 7, well, I just need to add something so that I get 2 over 7. Well, this would be technically 7 over 7. Oh no, 49 over 7. Okay, technically this would be 49 over 7. That's how we get the 7. So we would need to subtract by, well, everything but 2, so 47 over 7. So our remainder, when q is 1, or actually I can't say our remainder yet because we still haven't figured a way to get rid of this. But there is actually a way to do that. We just go minus alpha squared. because that would technically be in the q of x. So we can do that. We can just say minus alpha squared. So we get minus plus and so this would be all minus, essentially. Minus, what is this? 2 alpha minus 47 over 7. Okay, and that would be our remainder. So maybe that's our solution here. Right? That our solution would be what is it? Be negative alpha, so our r would be this, and then our q of r would equal the q of alpha. Now, can that be represented in this? In our polynomial? I think it can be. We just say that it is a polynomial, right? Like this is a polynomial. Okay, what was it? So let's see. We just say Q is our polynomial. So this would be 2 alpha minus 47 over 7. Now, generally you wouldn't use negatives because generally in a smaller field like something like x to the prime of 2, we have a characteristic of 2. So when we hit 2, you just have to add something and it becomes 0. But here, we don't have a characteristic because there's no characteristic 0 here. It's just q of x is x4 over x plus 2. So this has no characteristic. This is just an extension. So this actually increases our q by a lot, in fact. So what this says though is that every element is isomorphic onto this. So what that means is that every element has onto, and it's a one-to-one. So for every element there's another element out there that'll work, and we just have a function that can do that. So that's easy to know. So this, what we can say is explain now I'm wondering, I guess my next question is maybe what they wanted is this in this form, and like that's what he's actually looking for, right? So like how can we represent this in this form? So how do you even get that form? Well, what they're looking for is 2 over 7 plus alpha over alpha squared plus 3 alpha plus 7. So this is division, but normally we don't actually divide, we multiply by the inverse, right? Anyway, so what they're looking for is, I'm wondering if they're looking for a solution such that x4 plus x plus 2, where this is alpha 4 plus alpha plus 2 times q is equal to this plus some remainder, where we don't know what the remainder is. Now that would be hecka difficult. So I don't know. And that's what the problem with this question is. So what is this in the representation above? Maple will be handy. So it makes you wonder if they mean in this representation or in the representation that we found, right? So what we said was, so what it says is that this is a root of the irreducible this. So essentially when we put alpha in here, plus alpha, plus 2, we get 0. Right? And then what we did was we said Q alpha, Q adjoined alpha, is isomorphic to the extension of Q of x extended by x4 plus x plus 2. And that's taking every element of Q, x, and dividing it by x4 plus x plus 2 to get every element. So what that would mean is, like, if I have 3, how can we get 3 from Q to the x4 plus x plus 2? Well, I'd have to get rid of all those elements, right? And so the remainder would have to be negative x4 minus x minus 2. And this is modular. So what modular implies is that this would be 3 to the Q, I guess. Where the characteristic would have to be 0, which means that no matter what, you'll never kind of go above Q. So I don't know. So that's a tough question. That's something that, like, we just have to kind of be weary of. Like, how do we solve something like that? Like what is it really asking for? It's very difficult to grasp, and I guess that's why it's worth 4 points. And the worst part is this is just 1 out of, I think, 12. So like these questions tend to take a long time for me, specifically because of that. And like I don't really know where to look for help, you know. But here we are. We have 2 over 7 plus alpha, alpha squared, 3 alpha plus 7, and we want to represent it conveniently, probably like this. So we take our highlighter and we want it to represent like this. So how can we represent this? Well, we just set this to Q of alpha such that we get 2 over 7 plus alpha, alpha squared plus 3 alpha plus 7. And we say Q alpha is actually equal to Q our remainder. So to really conveniently represent it, we just had to find a polynomial where this is true with this. So what we can say is Q. So yeah, I think that is our solution, where Q is 1. So our remainder is definitely negative alpha 2 minus 2 alpha minus 47 over 7. And so Q alpha is going to equal QR and QR, so what we say is in here, so which is also Q alpha, which is also another thing of Q alpha, and this is a modular of x, essentially, of x over x4 plus x plus 2. So we represent it like this, and then we just have to find this. So Q alpha, where Q alpha is, or Q of R, such that Q is in Q, where the degree is less than 2. Or our degree is 2 less than n, where n is 4, I believe. And I think that would be our solution, or close to our solution. And so we just had to put that in. Okay, so I know that's all messy, but this is why we used LaTeX, to make it a little bit easier. Let's see. So where were we? We were on question 2. Where is question 2 again? Question 2 is right here. So I'm just trying to think. What's the mod of Q? I don't even know. I don't think it's anything really. One second, I'm just looking up something real quick. So like, I know it takes me a second to, I have to look up things and everything, because like, the fact is so normally you'd say 2, but there is no mod of Q, so Q is what? So what can we say? Why don't we represent this in a different way? Like, let's just take another look at this real quick. We can say that Q of alpha, the degree of it, actually this is just Q, is equal to what? The degree being the highest degree for the most minimal polynomial. Now, our degree is actually 4, so what we know is that the highest polynomial that's irreducible, or the lowest polynomial that's irreducible, is this. Okay, so this is actually what we know. That's a cool fact. That's actually kind of helpful, because what that means is that's our most minimal polynomial, such that this is equal to 0, and that's just information. At least that's something, you know. That's more than what we have, and what that would be represented on here is a line 2q, where this is 4. Okay, and that would make that a finite extension. Okay. Okay. So when we say we're mapping this to this, what this actually means is f, or q of alpha. What we have is an isomorphism, a function of q of alpha, where it goes onto q of x over x4 plus x plus 2. And then we have this, where we have the function, which is our q, and this equaling our f, or our q of x. So what we'll say is this is q alpha. Okay. And what that could mean, and I think this may be where we're actually looking for, because right now our q alpha is this right here. And what we want is our q of x, which would be what? Or what we want is q alpha. Oh, actually, I think I know what this is. What we want is q of a alpha to be represented such that that's what we want representation, where c is equal to anything. To sub c n minus 1. And it's asking how we can represent this in this form. Now, if this is equal to this, and that's what we want. So that's a really difficult thing to answer. Oh. So, I think I've figured it out. Okay. So it says to use the isomorphism. Okay. So let's clear this up. Let's clean this out. Okay. So with the above observation line, which you can't see unfortunately, sorry, but essentially it could be possible, but there is an easier way to do this. Use the isomorphism supplied by the theorem. The element for us is this, is our isomorphism. And what we have to do is use the Euclidean algorithm. Interesting. Okay, so what this implies is Q alpha is our X. So what we have here is 2, 7 plus X over X squared plus 3X plus 7. Okay, so we use this fact, and what we want to do is find everything such that this is equal to something else. Okay. .3. Let's just look at 14.3 because I don't fully remember 14.3. Okay, let's go down. Okay. By lemma 14.04, we just need to calculate the remainder upon division by x squared. .04. Okay. And this is the problem with this kind of math. It's just so complicated. You have to go through like so many things. Okay. So 14.04 says, suppose F is a field and P is an big F to the X, a polynomial of degree greater than 1. Then if F is an F of X, then Fp is equal to Rp, where R is the remainder of F upon division by P. If F is not in G, F of X is a degree less than P or equal to 0, then Fp is not equal to G of P. Okay. Well, what that says is that we're just looking for the remainder. And that, let's see. Oh yeah. and it's equal to its remainder. So, which we were actually describing. So, we need this to equal the remainder. Which would be pretty difficult because, well, there's an inverse function in there. So I might actually need to use maple. Okay, so let's go back to where we were, and we're gonna probably have to use maple. Yep. So I'm gonna open up maple. Okay. Oh, look at that. So we have our maple. And what we're going to do is group common denominators EX. Okay, so what we have is our 2 plus 7, or 2 over 7. Plus x. He made it quite difficult. He wanted us to use maple. And this is actually multiplying the inverse of x squared is 3x plus 7. Oh. Plus 3x plus 7. And so that's one. That's just one. It's disgusting, it's ugly, it's gross, but that's what it is. Next is we actually need the irreducible, which would be x to the 4 plus x plus 2. And then we just have the remainder. And I don't know what this S is for. Okay, and then R is going to equal. Oh, okay, that's what we wanted. I'm actually following the instructions that he left here, and it's telling me it's R. That's great. It's just makes my day when things like that happen. You know? Oh, I know why. Because I missed X. I actually don't need that. I need it here though. Invalid argument. That is cool. That is so cool. I like that. Let's find out why it's an invalid argument. Oh, it's not going to go to the actual class or group common dex. Greatest common denominator for exponentials. It's going to just bring me to an error. Okay, let's just double check that I have everything right here. X4 plus x plus 2, yeah. We have x squared plus 3x plus 7, correct. And 2 over 7 plus x. And yes. Nope. We didn't have X and it gave us 1, which is what we wanted. But now it's not giving me anything for R. Like at all. Ah! Oh! Oh, oh, oh. Hmm. So we want to find the greatest common denominator. Oh yes, now it's coming back to me. Let's try this. Why don't we look up greatest common denominator polynomials. Maple. We could just go like this. Let's try this. Let's just see what happens. Hi.
Some nachos.
Yeah? Sure, I'll have some nachos.
Oh, I saw you were streaming and I was like, this bitch. And then I was like,
oh.
That's Ew.
Ew.
You're gonna lose me. I was just thinking,
Probably, I don't know. Are you watching right now?
Nope.
I have one viewer. I don't know who it is though.
I feel like it always says one viewer.
I know. Okay. What are you doing to my armpit?
Tickle. That's why. I just did one assignment though. My short, easy assignment.
Yeah, I'm doing a long assignment.
Yeah, I think I'm gonna try to do another English assignment, or at least start it, cause like, I don't know, it's due Wednesday, but I actually have quite a bit.
Mm-hmm.
I have to watch a 2-hour film.
Okay.
I was on my day.
I know. Okay. So, the greatest common denominator. So what he does is he says that we find the greatest common denominator between these two polynomials. the one that's irreducible, and the one we have. Now we're saying that this is equivalent to what we had on this page right here. It's equivalent to the x's because of how isomorphism is. Because our alpha is our x. Alpha is x. So these are elements of x. And we want to find the greatest common denominator right here, which will equal our remainder. Now, normally what you would do is you would multiply this by something to get as close to this as possible so that we could reduce some elements. And then we'd take the remainder, and then we'd take this, whatever we got our q, and we'd shift it one over. And then we'd do it again. And then we do it again and again until we found 0, and then what we do is we'd find something to equal it. So this is where maple would come in handy, because maple is supposed to be able to do it quickly, but it's not giving me anything. If I do this, arguments should be polynomials. Arguments are polynomials. So I wonder. Okay, why don't we just do that instead? See if that helps. Like, it shouldn't help because honestly we're not changing anything, but okay, error in greatest common. The optional third argument given was x, which is this. This argument to GC is for returning the cofactor. It is not specifying the variable in which to compute. See, I'm just so confused. Arguments should be polynomials. Oh yeah. Invalid arguments, obviously. See, I'm trying to do exactly what, well, my teacher did. What's S in this? 0. R is nothing. Oh, this is so painful. Give me something. Let's test this out. Let's just copy this, get rid of this, and literally do what he did. See if that changes anything. X plus 1. We're going to change our irreducible to... We're literally going to do what he did. Yeah, the right. Yeah, the right. That's no way. What is going on here? Why, oh why does it work for him? The instant I try, I get nonsense. Okay, this is all working. Let's just change a few things real quick. We're going to go with our reducible that we've selected, which, not our reducible, our just 2/7. Oh, you know what it might have been? The 2/7. Times. Let's just nope. What we're looking for is x to the 2 plus 3x plus 7. Yep, that's about right. We've got a solution. Hey, it finally worked for us. That's a disgusting looking solution. Oh my god, it makes me want to puke. That looks so gross. That actually looks so gross. Why does that look so gross? What's up? Okay, so ew. That looks disgusting. Okay, so thus R, the corresponding opponent's class, is the inverse of 1. Okay, and then what we'll do is we'll test it. We'll say there's so many wires here and it's actually the most irritating thing. Stop getting in my way. Okay. Okay, so this is what we're looking for, and his solutions don't exactly provide answers because they don't exactly look like solutions. So what are we making this equal? Alpha. Oh, alpha is nothing though. We can't just... So is that our solution then? That's my question. corresponding equivalence class. This would be my corresponding equivalence class, essentially. Now, to verify, let's see. This is our Q alpha. So yeah, this is our class, except for this where every x is, we replace it by an alpha. That's our corresponding class, and that would be our answer. Maybe I can just include this. Let's see. Okay, so I see what they did. This hate wires. Hate them. Hate wires. Okay, so let's get rid of this. Oh no, we're here. So what this does is it essentially subs it in. So what we're gonna actually sub it for is B, where B is a representation of alpha, and this is x plus 1. No, we're subbing it into here. Okay, so B's are alpha. Oh, that can't be our answer. I just realized why not. Why can it not be our answer? Because someone, aka me, messed up the calculation. No! Are you telling me that there is no answer? Oh, that's why. Because it's representing it like this. Ah, okay, okay. That shouldn't be like that, but what we're gonna do is we're gonna defeat this by changing this to actually be this. Crap. See, this is what this shows right here. And this is what he wants us to do. And we get an invalid argument. Why do we get an invalid argument? Because why? Because there is no greatest common denominator between the two. So we know this works. Like, we know this works, but it's not working. That's irritating. I think what I actually have to do is multiply. This by this. Ah. Because essentially what we tried to do there is we tried to take this division, but what if we multiply both sides by it? Well, that makes it harder, for sure. Then we find the remainder, and this would be the remainder. And then we'll do C, so we use B, subs into R. And that's our representation. That is a easy representation. Now, I don't know if that works. The problem is, and this is a problem, is that I don't know. What am I saying here? So, what exactly is happening? We are saying that this is the greatest common denominator. Such that it equals 1. I don't know, it doesn't feel right, you know? Ooh, actually what I should do is I should check this out. And it doesn't simplify to 1 though. Look, it's not simplified to 1 at all. So it should simplify to 1. Okay, like why is that though? Like if we take his example, we take Q as 1 and we have x3 minus 2. Then our remainder is 1, 3, x2 minus 1, 3, x plus 1, 3. Okay, so what we do is we test this out. We get x3 minus 2. And does that work? Well, no, it does not. Where did this come from? So I'm kind of confused. Let's just go look at 14 again. Because obviously my understanding is not as strong as I want it to be. So what we're going to do is we're going to go through it again. Should be a little higher. 1 second. Here, I'll bring it up for you. Okay. So. So let's see. What we have here is this. Okay. So if we want to get 1, okay, what this is saying is when we take 1, we take Q, the remainder is going to equal x3 plus 2x squared plus 2x plus 2. And this is to the p, which is this polynomial right here. So how do we get that? Divide by x2. You'd have to multiply by x3. You'd multiply by x first. And that would give us x3 plus x squared. And then this would come down. But that's not our answer. So I've never really understood where this comes from. Like, this one makes sense to me. Because essentially when we want 0. Oh no. Okay, well, why don't we just take a look at this? So this is the definition that we're trying to figure out right now. Okay, so this is modular math. Essentially what this means is f minus g divided by p, or f equals g plus q of p. Now, this is what the lemma is saying. Suppose f is a field, p is an f of x, a polynomial of degree greater than 1, then if f is an f, big F of x, then f small f p, which is the mod of p, is equal to the r of p, which is r is the remainder of f upon division by p, where r is the remainder of f division on p. So what this is saying right here is when we have this, f of p is equal to r, the remainder. So this would be our remainder and this would be our f. When f is equal to 0p in here, okay, what would we need? Well, in order for this to be true, oh, This is P. G plus QP. Where QP is our remainder. Is this saying that QP is our remainder? I'm wondering. It's difficult to know. This is f of x mod p. So our mod is this. Okay. So when this is equal to this, what do we get? We get 0. I'm still kind of confused. Okay, let's see. My understanding is much different than what I thought this was. Okay. So if we want 1p, we have this right here. Why does this work? No. Okay, so they are just equivalent paths with representatives r, where r is 0 or degree r is less than 2. So when degree r is greater than 2, what do we get? Okay, so let's see. What did they do here? Okay, so this is G's our remainder. Okay. Then QP. So yes, when Q is equal to what? It depends on what Q is equal to. So if we make it 0, then if we make Q equal 1, then this would be our answer, because this should be our equivalence. So this is our 0 right here. Now, if we still have Q as our 0, then why does this become 1? When we pull the 2 out, we'll have x3 plus 2 This part becomes 0. But this part is what? Is that our 1? I thought I understood this, but now that I look at it, it's like I don't think I understand it as well as I thought I did. So we have q of x over 2. This is x over 2 f minus g. For a given row, construct a different second entry. So, like, my method doesn't exactly exclude me from being right. It's just, I don't quite understand how this is equal to this. Okay. Now, the mod is this. Okay, so that's what I have to remember, that the mod is this, so that when we get to this point, when we multiply to this is going to equal 0, right? And this is also our remainder. 1 second. Yes, this is our remainder. Right here. So, let's see. For this, okay, so if I want 0p, we have pq and r. And p is our x squared plus x plus 1. Now, we could have 0, in which case then r is 0, and that makes no difference. So let's make q equal 1. Well, this would be 0 by itself plus r. So you could have x to x plus 1. Now, if we wanted 1, now p is not going to change, so this is x squared plus x plus 1 times q plus r, and we want 1p. Okay. If we have 0, well, if we have 0, we just need something that equals 1. If we have 1, then we have this x squared plus x plus 1. Now this should equal 0 too, right? I'm just so confused right now. What if this is equal to? Now, no, we just want 1. So, r could be what? 1x squared plus 1x plus 2. So this becomes 3x squared. Now this becomes zeroed out because of the z3 right here. That's an element. So that zeroes out and we end up with 1. So that works, but my question is why does this work to the p? Like, that's just something I don't understand. I don't understand how increasing the degree gives us a 1. Okay, this makes sense for this. Okay, so what this ends up doing is we have 2x squared, 2x plus 1, and we add this. So this gives us 3x squared plus 3x plus 3, which is all going to be 0. Okay. Here is the problem. The next problem is, what about this x3 that's left? What we have is 1p equaling x to the cube to the polynomial. Why does these two things equal each other? Because we have x squared plus x plus 1 x3. That's 0, and then we get our x, which would x be x plus 1 as a remainder, but that wouldn't work. See, I don't understand how this x3 gives us a 1p. Or how this x4, x3 gives us 2p. Is it just because the cofactor, like the thing above it, is equal to 1? Then there's this. And this is equal to x. Let's see. 2x squared is 3x squared, which is 0. 1 is 2. Okay. Well, then what we have left is x3x plus 2. Yeah, I will. Okay. I'm gonna take a break. I'll be right back. Mm-hmm. Let's fix this real quick. Oh, it is right. Nice. Okay. That's cool. Okay. So this is what we're still trying to solve, right? Now, we tried using Maple, and Maple does not work. Okay. And the reason is because we are looking for the greatest common denominator for this. Okay. Oh, wait, 1 second. We want to get rid of this. Now, this won't have a solution. So what we got to do is we got to figure out what this is in mod P. First of all. So what we have here is x2 to the 7. Actually, plus 2 to the 7. Now, let's just check our perusal 1 second. So what we said was that this corresponds to this. So our alpha corresponds to our x. So that's what we're saying. Now, okay, that's what we want it to correspond to. Excuse me. So the next question is how can we find the greatest common denominator between the two? So this is something that would divide both things essentially. So when we look at x3 minus 2, we divide it by the x squared one. Like, that's an actual solution, right? So we have this, a equals this, and we're multiplying it by this. So essentially, you end up with 1. And that's because why? Because our remainder is this. So in this class, we end up with 1, which would be, what are we looking for? Our inverse? Yes, so our inverse, so this times this gives us 1. So that's why they simplify by multiplying. Okay, so that makes sense. Okay, what we're looking for is just a representation such that this can be represented in or we say C1 alpha. No, actually C1 alpha naught plus C2 alpha 1 plus C alpha. Now this would be degree 4, so this means that this would have to be degree 3 or less. Okay. Because based on, what is it? This principle right here. Where the degree of this is 4. Yeah. So the minimal degree is 4, so we need something such that, and this is what we're looking for. Okay, this is what we're looking for. So we need this in terms of that. And we want to do it by finding the greatest common denominator. Okay. So the greatest common denominator, how do we do that again? Now, it's the Euclidean algorithm. Can we use Maple for the Euclidean algorithm? Okay, so it's supposed to try to find the greatest common denominator here. The problem is this. It does not want to accept that. So how can we use this in that? So this will not work. I'm pretty sure I remember it. Okay, let's use perusal. Euclidean algorithm was first introduced to where? I think right here. No. 5 and 6. Let's check that. Nope. Okay, let's go back to 3 and 4. Of course. Ooh, that looked terrible. Okay. Here we go. So, what we do is we let A equal 2 over 7 plus alpha over 3 alpha plus 7. And then we let B equal x4 plus x plus 2. Okay. And this is what we want to do. In order to get x4 plus x plus 2, we need something such that... Oh, okay. Plus 2 over 7 is xp 2 plus 3 to the xp plus 7. So in order to do this, I want to get rid of this right away. There's no way I wanted to keep that, so I would multiply by x squared to the p plus 3 to the xp plus 7. Because that way I'm getting rid of this. So my q would be that, and then I just need to add stuff to get this, which would be very simple because what would I would do? Let's see. Well, then to get this, what I would do is add 5. I need 2, which is 14 over 7, so I need to add 12 over 7. And x4 plus 12 over 7. And that would give me that. And then when I add this, this is what will end up happening. This moves over here, x plus 2 over 7. And this time it's x4 12 over 7. Then I multiply it by another q. Now this q, I want to try to get rid of this x4. So what can get rid of? So in reality, our greatest common denominator is this. This is what we want, right? So with that being said, with maple, I actually just get rid of this. And that would be our solution. And how can we test this? Well, So what this says is that the greatest common denominator is equal to 1, which means that there is no way, there is no polynomial. It means that they're prime to each other. It means that there's no polynomial that is equal to each other. So the remainder, though, is what's going to give this. So when I add x4 to this, I'll end up here. And I just want to double check that's correct. I'm wondering if this is our like this is our cofactor, right? Or is this just, I'm wondering if this is our cofactor. Eek. Oh, so like Nathan. This is our remainder. What's this? This is what irritates me, is that I don't maple. I don't know the inputs of everything. Okay, so we have unevaluated names. Or G's the monic. Okay. This is the song I wanted to listen to. Oh, this is degree T and degree S. Okay, so it's S. Just S. Okay. So this is our cofactor of x. So when we multiply it here, we get 24,1, 4132. Now, what we're left with is x squared minus 49x and this y. One second, I'm gonna check something. 2 to the 7. X plus 2 over, no. So this is P, and we say that is going to equal It's just confusing, that's all. Okay, so is equal to 1. R is equal to this, our remainder. So what this means is we have 1/3 x squared. What's s in this situation? Let's see. X plus 1, x3 minus 2. So S is our cofactor. So we get negative 3x3 minus plus 2 over 3. Okay. Now, plus 2 over 3, that gives us what our gives us 1. Oh yeah, that's what we want. Okay. Then what we have is negative x squared minus 1 3x. Okay. Now, because what ends up happening is we have negative 1 3 over x cubed, right? 1 over 3x squared minus 1 over 3x. Now, this will give us our 1, but how does the rest of it give us our x? Right? I just don't understand it. Like, if we multiply this by negative 1 over 3, then we get negative 1 over 3 x cubed minus plus 2 over 3. Now, 2 over 3 plus 1 over 3 is going to give us this one. How does negative 1 over 3x3 plus 1 over 3x squared minus 1 over 3x give us our x? That is my question. That's what I'm trying to solve here, this part. Well, it's mod p. So this must be equivalent to x in mod p. So what that would mean is, if it's equivalent, that would mean what? That would mean, 1 second. 1 over 3x squared minus 1 over 3x plus 1 over 3 is equal to x. With mod p, and that would mean, to find that, you would have to do what? It would, the only way you'd know that is by doing everything first. So the first thing you'd have to do is show that, which is x3 minus 2 plus no, not that part. It would have to be this part. The negative 1 over 3x cubed plus 1 over 3x squared minus 1 over 3x. Or q is equal to this is a what? Plus 1 3. At 0, no. At 1, what do we get? This would have to be 1/3. Now that would 0, but then we still have this and this, so I'd have to multiply by this. So 1 second. Let's just find x. We have this here. So for just x, we need -1/2 plus x squared over 2. If we change, like, let's make s. I don't know. Zaricia is here. This makes things so difficult. I just don't know. I feel like I'm getting more and more confused the more I try to do this question. The greatest common denominator. Oh, wait. Oh, that's right. That's not how that works. Essentially what this is saying is x plus 1 times our r, which is 1/3 x squared. This isn't a remainder. These are our cofactors to make this equal 1. And this is why I'm getting so confused. So when I multiply this out, I'll get 1/3 x3 yeah, and that's going to get rid of everything, and that when we add everything up I get 1. Okay, so when we're going over this, thus r to the corresponding equivalent class, is this. So this is our r to this, and that's our remainder. And that's after doing everything. See, but here's the issue, is that this is not exactly, it's not, we're looking for this times some r plus x4 plus x plus 1 times some s equaling 1. That's what we're looking for. Now I can multiply everything out and then by this. But that would make this equaling this. So how would I do that though? I'm sure there's a way to do it. I love this one. Okay. No. Oh, extended Euclid algorithm for polynomials. That's what it's called. GCDX. The issue is that this assumes it's equal to 1, right? Now, you can't put a division in here. Do 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 do. Normally, what you'd do is you'd multiply all this by this, right? You multiply here and here and here. And what that would do is change everything. The problem is that I don't know how to make that equal anymore. Like, in Maple, what if I made it equal 2? Like, that's essentially what happens, is that I made it 1 equal 2, which doesn't make any sense. And then change this. Oh no, it's the 4th. Okay. I don't need these. I was just copying what he was doing. There is nothing here for you to be mad about because it's no longer there. Yeesh. So this would be our remainder, right? This would be our R, and our S would be what? Not that it matters. Okay, so to double check this, all we have to do is multiply it. So 2401 times 4132 times x4, okay? This times that x will be 0. This times x squared, yeah, and it's because of the 7, I'm guessing, which is, we can't divide even further. And the reason that this works is because this part, when we're doing this, we take this part and we make it equal, and we start the Euclidean. We can just make Q equal this, And once we do that, it doesn't even matter because after that point, we just solve. So the divisible part makes no difference, right? It's just meant to confuse. Okay, so now we have the solution. Okay. So let's solve it. So for this one, what we're saying is let r minus 1 equal x plus 1. Okay, that's what we said. We're making it equal. Oh my god, this wire is in my way. Okay. And then and r equaling 0 to equal well, what we're going to do is this. Since what we're going to do is since what's with the double? Oh, I'm on the wrong one. There we go. Is that center? 1 second. I gotta test this. It does. A simple centering. Oh my gosh. That's awesome. He just taught me something really useful quickly. Cool. Now what we're gonna say is therefore equal to itself, like essentially again without the R naughts. We don't need that. And then we just gotta close it. Okay. Generated it. Oh, here we go. So essentially what we're saying is because this is isomorphic, this alpha is actually equal to x. Therefore, r naught, which equals this, is actually equal to this. Okay. Now, we need to figure out this representation. Now this is problematic because again, of the issue, but 1 second. I'll look up how to include this. Okay, anyways. So is equal to this, actually equal to this. Now, this isn't a problem. I can't believe this centers. That's crazy. Okay. This becomes r minus 1 equaling r minus naught times q plus r. Okay. We should say r2. Wait. So we multiply by q to get rid of this. Now this is 276. We find the remainder, and then we take, which will give us our common denominator between these two. Here's the issue. Actually, we're going to change this. Okay. So we're actually going to get rid of all that. We're going to do this because we might need this. It takes a little bit longer, but it's used for creating a space that lines up everything. A math space, essentially. And then what we're going to say is we're going to tag this. And we're going to make it equal to this, way over here. We just gotta put it, because even though this is a math space, the tag is actually not in a math space. It pulls it out. It pulls into a talking space. Let's see. I'll be aligned. Do. Yeah, that fixed it. So now we have this, right? Do. Okay, we're gonna actually end that sentence, and then we're going to go to the next sentence, and we'll say let. See how well that looks. There we go. So where Q. Oh, we need to get rid of that -1. We'll say instead of that, where. Okay. Now, what that does is take this away, and it just makes it so that we can go with this and this. Now, here's the issue with that, and the issue being is that we are no longer working with just this element. It's actually, we've changed this element, right? So R2 or our R0 will now be equal to this, and we want to find a cofactor or a remainder such that greatest common denominator between this and R2. I believe. Now R2 will be what? We need it to equal x4 plus x plus 2. I'm gonna change this too. Hi, honey. I know, I heard him.
I don't even know what I want to do. My head hurts so much.
Mm-hmm.
It's making it really hard. I just had to read a million things, and I don't think I can bring myself to do the assignment yet. Let's do Wednesday, but...
Okay, so that gives us part of the solution, I feel like. Now, this is where we're supposed to find the greatest common denominator. where our remainder is equal to that. Bum 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 ba dum dum bum ba dum bum bum bum. I'm just thinking for a second. Just trying to visualize this. Okay. Well, our next step is we have this now. We have this x4 plus x plus 1. I'm pretty sure it's 1 plus 2. Equaling sx plus 2 over 7. And we need a remainder to make it equal here, essentially. So our remainder is going to equal x4 minus x. And then we need to get rid of, oh, we need to make that, so 12 over 7, plus 12 over 7. Now, we pull this over, and we want to try to get rid of many things. So we get x4 minus x plus 12 over 7. And this is where we could try to do a cofactor, I think. So why don't we take a look at Maple for a second? Because I think it's not this we want to make a cofactor with, because we've changed the game essentially. So oh, interesting. Let's get rid of that. If we look here, we've changed it. Oh. Even though we've essentially changed what we're looking for, my question after that is, what do we do about the division? Do we just divide under it again? Yeah, we would. We can find the greatest common cofactor and then divide by this. We could divide by this. Not by this, sorry. We can divide by this again. And that would be it, because we just put it back. Okay. So is that our solution? Okay, so essentially what we did is we said this. Is that r negative 1, as in x4 plus x plus 2, can equal... Wait, but does that make sense? I'd have to look up Perusal one more time, just to be sure. Let's go back to polynomials, or even just over here. Yeah, so what we do is we let the greatest common denominator be these things. Ah, yeah. Okay, so okay, so we found our solution. Yeah, sweet. So what we said, where are we? I feel like I kind of got lost here. Where am I? Right here. Okay. Okay. And then this is actually one. Okay. Where is equal to, now what did we say it was? We said it was minus x plus 12 over 7. We'll do fracs. Okay, 12 over 7. That'll give us a fraction. Oh no, I forgot to end the math area. So and q, and let's not do and, we'll do any number. Okay, now this is important because essentially what this says is that these don't matter in this situation, because what we're going to say is that since r to the -1 to the r of 0 is equal to of 0 to 1 -1. Where did it go? Did I close Maple? Or not Maple, Perusal? There we go. Oh. One second. I feel like I just had it. I think what the amount was this right here. So Rn minus 1. I just said it's not true. Oh. B plus QA. B plus QA. So if we make our A equal this, then we get X B equal that equal this, and this is our A, then we get 4 plus X plus 2 B plus QA. So the greatest common denominator of this. Oh. Okay. So I don't need this part. This part here, technically. So that would make this. Okay, so what we actually need. 1 second, let's just double check this. This is X. Yes. Yes. So this is X to the 4 plus X plus 2 now we multiplied by Q and we minus X to the 1 second, if I wanted X to the 4, no. We want X to the 4. We have X. We want 2, so I just have to actually. Oh! I need to add X, okay. So X4 and then. Oh, 12 to the 7. This is X2 to the 7, right? Yes. (12/7). Oh. Interesting. One second. That makes sense because it's what I just did with solve for it. Okay. E plus QA. We don't need B to be anything. Suppose I don't do that. Whoa, oh wait. Okay, well, I don't know. Oh, that's +2. Okay. What do we need? So this is +2, yeah. I guess technically I could just multiply everything by this and then find the remainder. I don't know. Okay, so this is true up to this part, okay? We don't need the minus part. Now this is x. We want to get rid of x plus 12 over 7, or x2 over 7. R2 could be negative x squared, which would get rid of that. I want to check something. 807,673. I might have messed up the numbers. Let's see. $341, $495. Let's do 341. 341, 495. $495. 11. So the greatest common denominator is 11. How did we find that again? Oh right, it's the very last one, isn't it? Right before we hit 0. Okay. Okay. And that's why this works, because the remainder, the greatest common denominator is 1. Or it would have been, but there's no greatest common. There is a greatest common denominator between these two. Okay, so this implies that this is it. One second. Wondering if it works the other way, like if we put it Zaricia? Oh no, hi honey.
Tell me why I already have to use a different pen.
I don't know. What do you do? Yeah. Well, let's check that actually. This is completely different than why does that have to be 2401 or 413? We want to find the greatest. We want to find the remainder from the Euclidean algorithm for x, r, and okay. Since we're looking for the greatest common denominator, greatest wait, GCD stands for what? Yeah, greatest common divisor. We look towards the numerator. I.e., we want to find the greatest common denominator of find the remainder of the greatest common denominator of this and this. Oh my god, that question took forever. The remainder r is equal to by Maple. So I can just copy that. Nope. And nope. Okay. I think we're almost down to a solution here. Oh. I don't like how that looks in the slightest. So what we're going to do is C dot. And what we're going to do here is frac. We're going to do this for everyone. This gets super tedious. No, I went down. I have to go all the way back. This is why it takes so much more time. Ah, yeah, there you go. Let's get rid of the C dot. That looks bad in this situation. Now this should make sense because it should be a degree less than 4, which it is. And we're actually going to show that one, and we're going to make it look nice up here. No. This is replace every x with not inverse, multiplied by the okay. Now we're going to take this. And we're going to change all the x's to alphas. Ooh, I forgot to multiply this by alpha. Or x. And this one is just by alpha. And then I need to find the bottom one, this one. Or this is gonna squish in properly. Nope. I get rid of the R. Brilliant. That took a while to figure out. That's 4 hours. It took me 4 hours for one question. It's so freaking depressing. Ah! Okay, we just have to calculate the minimal polynomial for this. Okay. I want to get through at least 2 questions. Okay, let's go here. So, we're on this question now. Oh, I think I've already solved this. Listen, C1 was negative 14. C2 is equal to 1. That makes sense. Oh, and then I needed a calculator for the rest. And then we have to do it for this. No, I haven't done that one yet. And then I gotta figure out how to show this. Show that this is algebraic over F, then so is G. I think it's based on this right here. This question's more based on this one up here. Okay, well, oh, I'm tired. Okay. Let's work on this. Okay. Okay. Now what do I want to do? Oh yeah. We're literally going to just copy exactly everything. Alright, assume hypothesis. Okay, we're gonna let g equal 7 minus the square root of, what is it, 5? Or 2 times the square root of 5. Okay, and then what do we want to do from there? Benign Bagan. Okay. Okay, it's going to equal the square root of 5. And then g squared is going to equal 7 times 7, which is 49, times 7 times negative 2 plus 7 times negative 2, so 14 twice, negative 28 to the square root of 5. And then square root of 5 twice, which is 5. Plus times the positive 4, which is 20. And what we're going to do is we're going to line it up with these. And that's actually going to equal 29? Oh no, 69. 69. Anyways, minus 28 square root of 5. Okay, so now we have this. And it's where C naught. Oh, I farted in so bad. Plus C to the 1 G. So this is G naught. G to the 0, sorry, G to the 1 plus C to the 2 times G to the, or to the square equals 0. Okay. End of line. I messed some up. I'm messing the line. What did I mess up, bro? End of line. End of line. Begin a line. Yeah. Let's just double check that this is actually the problem. Interesting. Oh, hello. Second end of line. And first end of line. Oh. Enumerate. Perfect. Through analysis, we can see C2 is equal to 1 C1. Ooh, I should probably make them big C's. Let's make them big C's. Feeling risky today. Do 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 is equal to negative 14, and we need this to equal 0. So seven times 14 is negative 98. 7 times negative 14, negative 98 plus 69. So C0 is going to equal negative 29. Right? Wait. Plus 29. Don't have to actually put the plus. And therefore, we are done. We have found a root. Now, is it irreducible over Q? That is the real question. We get 1, negative 14, 29. We can see that it's irreducible. So our polynomial is two minus oh, actually it's just x2 minus 14 plus 29. So okay. Can we see that this is an irreducible polynomial? Is it in this line? Oh, right here. Okay. Now, is that irreducible over Q? Can we make a number from it? We could do set over 2. Let's see. That's 14. Let's just check it. The roots of this. Let's just see if we can find the roots. So negative 14 plus or minus 14 squared minus 4ac, which is 29 over 2 essentially. So let's see, 4 times 29, 116, 14 squared minus that is 80. The square root of that is 8. which is irreducible, which is the square root of 80 40 times 2, 20 times 4, times 4. Five times 4, so this is actually 4, 5. 114 divided by 2. Oh, no. So this would be -7 plus or minus this. So that's our answer, which would be this. Which is not, so which is irreducible over Q. Through the quadratic formula, we can see that our polynomial is reducible over but not Q. Wait, I just want to check something. That's not it. Oh, which is our minimal polynomial. Okay, good. It's not monic, but okay. So therefore it's our minimal. Therefore is our minimal polynomial. Done! Okay. Then I gotta calculate the minimal polynomial of this guy. Calculate the minimal polynomial of y plus 2 in y squared plus 2y plus 2 over z3 using this technique. So that would give us 2y plus 2. So when we squared it, two y squared plus 2y. down. So what do we need? Bring me down. Coming to Zame soon?
Soon? You gonna quit soon?
Mm-hmm.
Yeah, I'm just I'm doing my notes for stuff that I'm almost done.
Next time, I'm just gonna go through the easy questions.
Huh?
Nothing.
Next time what?
Nothing. I'm not talking to you.
Oh.
Suppose alpha is a root of this. Okay. Show that every male element of Q and A has degree 1, 2, 3, or 6 over Q. That's... is a root of this. So this alpha is a root of this. So this becomes 0, 0, 0, 0, 0, 0. Okay. Bring down one. Now we're not saying. Oh. Now this is Q alpha adjoined. Q adjoined alpha. Now we don't know anything between here and here except that this is a root of that. What does it even mean? Show that every element of Q adjoined A has a degree 1, 2, 3, or 6 over Q. How would I do that? How would I do that? How would I do that? I don't understand what I would do. How would I show that? So here it is. We have alpha is a root of this. So that means alpha makes this 0. Okay, Q of X. How does that tell me that show that every element of Q and alpha has a degree of 1, 2, 3, or 6 over Q? What? Damn, that hurt. I wonder if it has to do with this. So what we say, Q adjoined X Now we know that this is 6. Well, we don't know what that is, so what we say, what we also know, Q of X let's see. Adjoin X, Q, adjoin alpha. Actually, this would be X adjoin alpha. Now, we know Q alpha is 6. Q of X we don't know. This is a question mark. Now, we also just have Q. This is a question. This is a question mark. Now, it's going to equal Q X and alpha joined now we know that this degree is 6. Whoa. We don't know what Q joined alpha and X we don't know what that is. We also don't know Q alpha so that's 2 variables. Now would this be 2? No, this would have to be 1. Oh. Now we know that is 6. What we don't know is what's this. 1 second. This is where we gotta look at perusal. What's this over here again? Oh yeah, this is what I want. Yeah.
Do you remember what Mom's measuring tape is?
What?
You remember what Mom's measuring tape is?
No. We haven't used it in a long time. Where is he? Let's you come say hi to me?
If you go in there, you'll see why.
Huh?
If you go in there, you'll see why.
Is he high as hell?
You should see.
He's naked? That's weird.
He's saying your name.
Zathan? I totally forgot. Okay. So I feel like maybe this is the way we're supposed to be going. Because then we just have to show that it's a multiple of two things, right?
Was he? Where was he?
Just entering Matthias's room.
He just wants to be included. Appreciated. Nobody appreciates. Oh yeah. It's okay, like he's being good. He's not doing anything, he's just sitting. Let him live.
Get the hell out of here. Try going into the door.
He was. He's being good. He just wants to know what's happening. His life. Don't do that. What the fuck are you doing?
Told you he likes it.
You're like picking him up. And he like.
You're just like,
You look like you're aggressively needing milk.
yeah, but like, he likes it. Look at his face. It's like, oh.
Does he though, or is he just submissive to you?
Yeah, they don't like the snap. I'm just snapping along.
She's just like, ah. Yeah.
Sorry, guys.
Ew, come here. I don't want to. Ew. Come here.
DVD.